Welcome, everyone. I'm excited to kick off today's presentation with a focus on the foundation. This is the first slide, setting the stage for what's to come. We'll be exploring the core principles that underpin our work, and I'll give you a brief overview of the topics we'll cover today. Let's get started. Let's talk about the foundation, which is really the extension of the base structures. Think of it as the support system that directly keeps everything in balance or in equilibrium. The foundation essentially acts as the ground beneath the structure, providing stability and strength. Now, the bed refers to the prepared ground where the foundation rests. It's crucial because a well-prepared bed ensures the entire structure remains stable over time. When we place an object on the foundation, our main goals are to avoid fractures, distribute the weight evenly, and support a uniform load. This helps prevent overloading any one part, which could lead to failure. By doing so, we increase the stability of the entire structure. An even and level surface is essential here. It ensures the load is spread out properly and the structure remains balanced and secure. In short, a solid foundation is fundamental to the integrity of any construction. It's about creating a reliable base that supports and stabilizes the whole structure. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at the causes of failure in foundations. One of the main issues is that soils tend to yield to pressure, meaning they can compress or shift under load, leading to instability. Shrinkage and compressibility of mortar joints are also significant. As the mortar shrinks or compresses over time, it can cause cracks and weakening of the structure. Unequal settlement of the subsoil is another critical factor. When different parts of the foundation settle at different rates, it creates stresses that can damage the structure. Horizontal movement of earth is also a common problem. Lateral shifts can exert force on the foundation, compromising its integrity. Withdrawal of moisture from the subsoil leads to drying and shrinking of the soil, which can cause the foundation to settle unevenly or even crack. Lateral thrust, which is the sideways force exerted by soil or water pressure, can push against the foundation walls and cause failure if not properly designed for. Disintegration of cement mortar, perhaps due to chemical reactions or poor quality, weakens the bond between the foundation and the structure. Lastly, the escape of soft soil beneath the foundation, often caused by erosion or improper compaction, results in a lack of support and potential sinking or tilting of the building. Understanding these causes helps us identify potential issues early and design foundations that are resilient and durable. When it comes to prevention, there are several key considerations to keep in mind. First, using stiff mortar is important, but it shouldn't be applied too quickly, as that can cause issues with bonding. After masonry work, it's essential to keep the structure damp for about 14 to 20 days to ensure proper curing and strength development. When loading a structure, always make sure it is within the safe bearing capacity to prevent settling or failure. In areas with soft soil, techniques like sheet piling can be used to provide additional support and stability. For retaining walls, it's crucial to manage water drainage effectively, because water not drained away can increase pressure and compromise the wall's integrity. Sometimes, extending the footing on the leeward side helps counteract lateral forces, especially in windy or slope conditions. To handle lateral pressure, reinforcements such as beams can be incorporated into the design. Additionally, placing a layer of mortar between the foundation and clayey soils can improve stability by creating a better interface and reducing settlement issues. Increasing stability can also be achieved by widening the structure itself, distributing loads more effectively. When constructing with stone and cement mortar, filling any empty spaces prevents weak points. And finally, when excavating, avoid trenches near rivers, as deep cutting or deep wells can destabilize the ground and cause unforeseen problems. All these measures are interconnected and contribute to a comprehensive approach to preventing structural failures and ensuring long-term stability. When it comes to the choice of foundation, the type of ground you're working with is absolutely crucial. First, we have solid rock, which is ideal because it provides a very stable and strong base for almost any structure. Next, we encounter ordinary soil, muram, and gritty gravel. These materials can be suitable, but they often require proper compaction and sometimes stabilization to ensure they support the load effectively. Then there's pure gravel and sand, which are generally well-draining but can be less stable on their own, so they may need reinforcement or mixing with other materials. Black soil is another option, but it can be tricky because it tends to expand and contract with moisture changes, so it needs careful treatment. We also need to consider the nature of the substratum, whether it's hard or soft. Hard substrata are preferable because they provide a firm foundation, whereas soft substrata might demand additional reinforcement or special foundation techniques to prevent settling or shifting. Understanding these different types helps us decide on the most appropriate foundation for safety, durability, and cost-effectiveness, tying back to the overall goal of constructing resilient structures. Now let's look at the loads on masonry, specifically the dead load. These are the weights that the structure must support over its lifetime. On this slide, we see a table that lists different materials and their approximate weights in kilograms per cubic meter. For example, earth and loose soil weigh around 1,600 kg per cubic meter. Brickwork is slightly heavier at about 1920 kg per cubic meter, while reinforced cement concrete, or RCC, is significantly heavier at 2,500 kg per cubic meter. Mortar and plaster come in at roughly 2,000 kg per cubic meter, and timber ranges between 800 to 950 kg. It's important to note that iron and steel are much heavier, at about 7,850 kg per cubic meter. This variation in weights helps us understand how different materials contribute to the overall dead load of a structure. Recognizing these differences is essential for accurate structural design and safety, ensuring that the foundation and supporting elements are properly sized to handle these constant loads. So, when designing a building, knowing the weight of each material helps us calculate the total dead load, which is a fundamental step in creating a safe and efficient structure. Now, let's talk about live loads, which are the loads that structures need to support during their use. Here, we see a table that outlines different types of buildings along with their equivalent dead loads. The dead load, as you know, is the permanent weight of the structure itself, but the live load varies depending on how the space is used. For residential buildings, the typical live load is around 250 kilograms per square meter. This reflects the weight of furniture, occupants, and other movable objects. Moving on, theaters and hospitals have a higher live load, about 500 kilograms per square meter, because these spaces often require heavier equipment and more furniture. Similarly, office buildings and schools also carry a live load of around 500 kilograms due to desks, chairs, and the movement of people. When we look at assembly halls and libraries, the load increases slightly to about 550 kilograms, accounting for larger groups of people and the additional shelving or seating arrangements. Factories and warehouses are on the higher end, with live loads reaching up to 1,000 kilograms per square meter, since these spaces often store heavy machinery and materials. Lastly, for flat roofs used as terraces, the live load is typically about 250 kilograms, which covers pedestrian traffic and light maintenance equipment. The key takeaway here is that the live load varies significantly depending on the building type and its intended use, and understanding these loads is crucial for designing safe, efficient structures. This table helps us see how different building functions directly influence the structural requirements and helps us plan accordingly. Now, let's take a closer look at footings. One key aspect is providing for an increasing width of the foundation, which helps distribute the load more effectively and ensures stability. When we project each step of the footing, it's important to offset it slightly, about 5 centimeters for brickwork and between 10 to 15 centimeters for large stones. This offset is essential to prevent undue pressure and to create a proper stepping pattern. The number of these offsets depends on the width of the footing itself, so wider footings typically require more offsets to maintain stability. When calculating the area of the foundation, we use the formula W divided by SBC, meaning the width of the foundation divided by the soil's bearing capacity. The area, A, is then the width of the foundation multiplied by 1 meter of wall length, or the width times the length of a pillar. In terms of load, W represents the total weight of the soil plus an additional 10% margin to account for safety and unforeseen loads. Lastly, the thickness of the concrete bed should be about 5/6 of the wall's thickness. This ensures a solid, level base for the wall and helps prevent settling or cracking over time. These principles all work together to create a strong, durable footing that supports the entire structure effectively. Let's take a look at the depth of the foundation below ground level, which is a crucial aspect for stability. The formula D equals 1 minus sin F squared divided by 1 plus sin F. Here, F represents the angle of repose, which is the steepest angle at which material remains stable without sliding. This angle directly influences the design of the foundation depth. The pressure exerted on the foundation, denoted as P, is calculated as the weight of the structure divided by the area of the foundation. Ensuring this pressure remains within safe limits is vital for preventing failure. Additionally, we recommend a minimum depth of 60 centimeters below ground level. This minimum ensures adequate stability and helps prevent issues like frost heave or surface erosion from affecting the foundation. By understanding and applying these concepts, we can design foundations that are both safe and efficient, supporting the overall integrity of the structure. Let's take a closer look at the ground layout or terracing process. As you can see, the center line of the main walls forms the largest triangle, which helps us establish the overall framework for the excavation. The intermediate lines are then added to break down the area into manageable sections. Pegs are driven beyond the lines of excavation to serve as reference points, ensuring accurate placement as we proceed. Lines are then marked out with a pickaxe, which helps us maintain precision when outlining the boundaries. Once these preparations are in place, we can begin the excavation itself. Starting from these well-defined lines ensures an organized and efficient process, setting the foundation for the entire project. This step-by-step approach is key to maintaining accuracy and control throughout the excavation. Now, let's look at the key steps involved in the initial stages of construction. First, we have trenching, which is the process of digging trenches to lay the foundation. This is a crucial step because it determines the exact location and depth of the foundation. Once the trenches are dug, we move on to the actual excavation, where the soil is removed to create a level and stable base. Next is leveling, which ensures that the ground is perfectly even, providing a solid platform for the subsequent construction phases. After that comes the footing, which is a thick concrete strip that distributes the load from the structure above to the ground below. It's essential for stability and preventing settlement. Following the footing, we proceed to lay the foundation itself. This is the base that supports the entire building. Once the foundation is set, we build the plinth, which should be approximately 50 centimeters above the ground level, or GL. The plinth acts as a protective buffer against moisture and dampness. To prevent moisture issues further, a damp-proof course is installed at about 1 meter above ground level. All these steps are interconnected and critical for ensuring a stable, durable structure. They form the backbone of safe and effective building construction, aligning with our overall goal of quality and longevity in our projects. Now, let's talk about bearing capacity. This is a crucial aspect because foundations are designed specifically to transmit the load from the structure above to the soil below. Essentially, they serve as the interface that ensures the building's weight is properly supported. Foundations are generally grouped into two main categories. The first is shallow foundations. These are used when the soil has good bearing capacity close to the surface, and they typically transfer the load at a relatively shallow depth. The second category is deep foundations. These are necessary when the surface soil isn't strong enough to support the load, so the foundation must reach down to firmer, more stable soil or rock layers. Understanding these categories helps us select the right type of foundation for different site conditions, ensuring safety, stability, and efficiency in construction. This classification ties into the overall theme of designing structures that are both resilient and well-suited to their environment. Let's talk about shallow foundations, which are actually the most common and cost-effective type of foundations we use. Among these, the most straightforward and economical are spread footings. These are typically square in shape, designed to support individual columns, but they can also be circular if needed. The idea is to spread the load from the column over a larger area of soil, helping to prevent settlement. This approach is quite practical and widely used because it balances simplicity with effectiveness, making it ideal for many building types. Remember, choosing the right foundation depends on the load and the soil conditions, but in many cases, spread footings are the go-to solution. Let's talk about strip footings, which are used to support wall loads. These are essentially continuous strips of concrete that run beneath load-bearing walls to distribute the weight evenly across the soil. They're a simple yet effective solution for supporting load-bearing walls in many types of structures. Moving on, we have rectangular and trapezoidal footings, which are typically used for supporting one or two columns or even a machine base. When supporting multiple columns, we often combine footings into what's called a combined footing. This helps distribute the load efficiently, especially when columns are spaced closely together or if the soil-bearing capacity varies. As referenced in McCarthy's 6th edition, these types of footings are fundamental in foundation design. The shape, rectangular or trapezoidal, depends on the load requirements and the layout of the columns or walls. Trapezoidal footings, for example, might be used when the load distribution or the soil conditions warrant a wider footing on one side. Overall, understanding these different footing types is crucial because they form the foundation of supporting loads safely and efficiently. They help ensure stability and longevity for the structure, aligning perfectly with the overarching theme of designing reliable and durable foundations. Let's talk about raft or mat foundations. These types of foundations are particularly useful when we're dealing with soils that have low bearing capacity or when the conditions are quite erratic or variable. The main goal here is to lower the bearing pressure exerted on the soil, which helps in preventing excessive settlement. By spreading the load over a larger area, raft or mat foundations reduce the risk of differential settlement, which can cause uneven settling and structural issues down the line. This approach is especially important in challenging soil conditions, ensuring stability and durability for the structure. Remember, the key idea is to create a uniform distribution of load to mitigate potential problems caused by the soil's variable characteristics. This concept ties into our overall theme of designing foundations that adapt to and work with soil conditions to ensure safety and longevity. Let's talk about floating foundations. These are used in situations where deep deposits of compressible and cohesive soil are present, and installing piles isn't practical. Instead of relying solely on piles, the building's substructure is designed as a combination of a mat and caissons, essentially creating a rigid box. This design helps distribute the load more evenly. The key idea here is that the weight of the earth displaced by the foundation is made to be equal to the total weight of the structure. This balance minimizes settlement caused by consolidation over time. This concept is from McCarthy's textbook, 6th edition. Overall, floating foundations are a clever solution when dealing with challenging soil conditions, ensuring stability while managing settlement effectively. All right, let's talk about deep foundations. These are used particularly when the soil near the surface doesn't have enough load-bearing capacity to support a structure. Instead of relying on the weak surface soil, deep foundations transmit the load downward. They do this by transferring the load through the weaker soil layers, often called overburden, down to a stronger, more stable layer beneath. This stronger layer could be bedrock or dense sand and gravel, which can safely carry the weight of the structure. So, in essence, deep foundations act like a bridge, passing the load through the weaker soil to a more reliable support beneath. This approach is crucial in situations where the upper soil layers are loose or unstable, ensuring the stability and safety of the building above. Remember, the key here is understanding the importance of reaching down to those stronger strata to provide a solid base, especially when the surface soil just isn't up to the task. Now, let's take a look at the different types of deep foundations. First, we have those used where the load-bearing stratum is no more than 5 meters deep. These are typically simpler and less costly options, but they are not used as much anymore because of the availability of more advanced methods. One common type in this category is the piers, which are essentially deep, column-like structures that transfer loads to the underlying soil or rock. Next, we have caissons. These are larger, watertight retaining structures that are sunk into the ground and filled with concrete. They are often used when the load-bearing layer is a bit deeper or when more stability is needed. According to McCarthy's 6th edition, caissons are a reliable choice for certain conditions. Moving on, where the overburden or the layer of soil or fill above the bedrock or load-bearing stratum is no more than about 8 to 9 meters thick, we see a shift in practice. In these cases, caissons often replace piers because they can handle greater loads and provide more stability for the structure. So, understanding these types and their suitable conditions helps us choose the right foundation method based on the specific site conditions and load requirements. Let's talk about piles, specifically those with a deep overburden, which is more than 8 to 9 meters thick. This means we're dealing with substantial layers of soil or other materials above the pile foundation, which can influence how we design and install these piles. There are various types of piles used in construction, and the placement methods can vary depending on the project requirements and ground conditions. Understanding these differences is crucial for ensuring stability and safety. As Craig discusses in the 6th edition, knowing the right type and placement method helps us optimize structural performance and manage the challenges posed by deep overburden layers. This is an important aspect to consider as we look at foundation solutions for complex projects. Let's take a look at the structural requirements to ensure the stability and safety of our supporting soil. Typically, a factor of safety against general shear failure is required to be between 2.5 and 3. This means we need to have enough strength in the soil to withstand loads without risk of failure, providing a good margin of safety. Next, we need to consider settlement. It's important that the amount of settlement is tolerable, that is, minimal enough so that it doesn't cause structural damage or interfere with the building's function. Differential settlement, where different parts settle unevenly, should be kept under control to prevent cracks or structural issues. Lastly, during construction, we must ensure that our work doesn't negatively impact adjacent structures or nearby services. This is secondary but equally vital, as construction activities should be carefully managed to avoid causing any harm or disruptions to surrounding infrastructure. All these factors together help us achieve a safe, functional, and stable structure while respecting the surrounding environment. So let's talk about bearing capacity. This is really about understanding how much load the soil can handle before it fails. The key question here is, how do we estimate the maximum bearing pressure that the soil can withstand? Essentially, we look at various factors like soil type, its strength, and the conditions of the site. We use these to calculate a safe limit, what we call the ultimate bearing capacity. This helps us ensure that the foundation we design won't cause the soil to shift or collapse under the load. It's a critical concept because it directly influences the safety and stability of any structure. If we underestimate, we risk failure. If we overestimate, we might end up with unnecessary costs. So, throughout this presentation, keep in mind that understanding bearing capacity is fundamental to designing safe and reliable foundations. It connects to everything else we're discussing about soil behavior and structural integrity. Let's take a look at the safe bearing capacity, which refers to the maximum load that a surface can support per square meter without risk of failure. This is a critical factor when designing foundations because it helps us determine how much weight the ground can safely handle. In the table, we see different types of soil along with their typical capacities. For example, Soft yellow soil has a relatively low capacity of about 5 tons per square meter, which means it can support only light loads. In contrast, compact clay can handle between 20 to 25 tons per square meter, making it more suitable for heavier structures. Loose sand supports around 15 to 20 tons, while compact sand can bear slightly more, from 15 to 25 tons. Red earth is even stronger, supporting roughly 30 to 40 tons per square meter. Gritty gravel is quite robust, with capacities ranging from 70 to 90 tons, and rocks can support a wide range, from 20 up to 150 tons per square meter, depending on their size and composition. Understanding these values is essential because selecting the right soil or improving the soil conditions can prevent foundation failure. It ties directly into the overall theme of ensuring safety and stability in construction. Always remember, knowing the soil capacity helps us design foundations that are both safe and economical. When the safe bearing pressure of soil is quite low, it often results in the need for very large and uneconomical footings. This is where improving that safe bearing pressure becomes really important. By doing so, we can design more practical and cost-effective foundations. One method is increasing the depth of the foundation, which allows us to reach firmer soil layers that can bear more load. Another approach is compacting the soil, which improves its density and strength. Draining the soil helps remove excess water that can weaken the soil's load-bearing capacity. Confining the soil involves applying pressure to reduce its volume and increase stability. Grouting and chemical treatment are also effective techniques. They involve injecting materials into the soil to enhance its strength and stiffness. These methods are essential tools in foundation engineering, helping us optimize the soil's bearing capacity and ensure the safety and economy of our structures. Let's now look at some methods to improve the foundation's bearing capacity. First, increasing the depth of the foundation can help. In granular soils, it's been observed that the bearing capacity tends to rise as you go deeper, mainly because of the overlying weight providing more confining pressure. However, while this method can be effective, it's not always economical because deeper foundations mean higher construction costs. Plus, as you go deeper, the load on the foundation also increases. So, this approach is most useful when you encounter a better, more stable soil layer at greater depths. Next, let's talk about soil compaction. This method involves improving the soil's strength by reducing its voids, which boosts its bearing capacity and minimizes settlements. There are a couple of effective ways to achieve this. One is moist soil compaction. Here, we moisten the soil and then compact it using hand rammers, mechanical rammers, or vibratory rollers. The key is to reduce the voids, making the soil denser and more stable. Another approach is rubble compaction. This involves spreading a layer of well-graded rubble, about 30 to 45 centimeters thick, over the foundation level and then well ramming it. If the soil underneath is particularly loose, we can add another layer of rubble, about 15 centimeters, and ram it manually. This layering and compaction process helps increase the soil's bearing capacity significantly. Overall, these methods, whether increasing depth or compacting the soil, are aimed at creating a more stable and supportive foundation, which is crucial for the safety and longevity of any structure. Now, let's look at some effective methods to improve soil bearing capacity, starting with flooding the soil. This technique involves inundating very loose sands to increase their bearing pressure. It's particularly effective in dune sands, which are difficult to compact otherwise. Flooding helps to stabilize and densify the soil, making it safer for construction. Next, we have vibration. Heavy vibratory rollers and compactors can compact granular soils to depths of 1 to 3 meters. When combined with flooding, where the soil is saturated to a depth of at least 1 to 2 meters, and vibration, sandy soils can be compacted very efficiently. This process results in higher safe bearing capacity and reduces settlements under load. The equipment involves using vibrators or platform vibrators, which typically have about a 1 by 1.5 meter base area with eccentrically loaded motors. By sliding these on the sand surface, assisted by 2 laborers, large areas can be treated without sophisticated machinery. It's a practical, cost-effective approach. Moving on to vibroflotation, this is a more advanced, commercial method that combines vibration with jetting. It uses a heavy cylinder called a vibroflot, which vibrates via rotary eccentric weights. Water under pressure is supplied through a jet at the tip of the vibroflot, which helps it sink into the ground. As it sinks, clean sand is added into the crater created on the surface. This method is particularly useful when supporting heavy loads over a wide area, as it significantly improves the soil's capacity. Another technique is compaction by preloading. This is especially beneficial when dealing with clay soils that tend to settle over time. Preloading involves applying a temporary load to accelerate consolidation, causing settlements to occur well before the actual construction begins. Once the settlements are achieved, the load is removed, and construction can proceed on a more stable foundation. Finally, we have the use of sand piles. This method is highly effective in sandy or soft soils. It involves driving hollow pipes into the ground at close intervals. The soil between these pipes gets compacted as the pipes are driven in. Then, the pipes are gradually removed, filling the resulting holes with sand that is rammed in to form sand piles. These piles act as reinforcement, increasing the overall stability and load-bearing capacity of the soil. Together, these methods provide a comprehensive toolkit for ensuring soil stability and safety in various ground conditions, aligning with our overall goal of creating secure and durable foundations. Let's now discuss some important methods to improve soil-bearing capacity. First, drainage of soil is a well-known technique. As many of you know, water presence in soil, especially when it's saturated, significantly decreases its bearing power. This happens because excess water reduces the soil's shearing strength. By implementing proper drainage, we can decrease the void ratio and, as a result, enhance the soil's bearing capacity. Next, confining the soil can be very effective, particularly when the safe bearing pressure is low due to settlements caused by lateral movement of loose granular soil. To prevent this lateral movement, we can confine the soil outside the foundation area by driving sheet piles around it. This creates an enclosure, effectively holding the soil in place and improving stability. Then there's grouting, which is especially useful for loose gravels and fissured rocky layers. The process involves drilling boreholes at strategic locations and then forcing cement grout through these holes under pressure. This fills cracks, voids, and fissures, effectively increasing the soil's bearing value by consolidating the strata. Finally, chemical treatment offers another approach. Instead of cement grout, certain chemicals are injected into the soil. These chemicals are designed to solidify and gain early strength, thereby improving the soil's load-bearing capacity. Together, these methods provide a comprehensive toolkit for enhancing soil stability and ensuring safe, reliable foundations. Now, let's take a closer look at bearing capacity failures. These failures occur when the soil or foundation material can't support the loads applied to it, leading to a failure of the structure's footing. There are several different modes or types of failure that we should be aware of. First, we have the general shear failure. This type happens when the entire foundation and the surrounding soil fail together in a shear failure, typically characterized by a sudden and catastrophic collapse. It's usually associated with soils that are relatively uniform and well-drained. Next, we have local shear failure. Unlike the general failure, this is more localized, affecting a smaller zone around the footing. It often occurs in softer soils or in cases where the footing exceeds the soil's capacity in a specific area, but the failure doesn't extend beyond that zone. Finally, there's punching shear failure. This type is common in situations where a concentrated load, like a column or a pile, causes a punching action into the soil, leading to a failure that looks like a punch or a plug being pushed through the soil beneath the load. It's especially critical in slab foundations and heavily loaded columns. Understanding these failure modes helps us design foundations that avoid these pitfalls, ensuring stability and safety for the entire structure. Now, let's talk about general shear failure. This type of failure occurs when the shear stress within a material exceeds its shear strength, leading to a sudden and complete failure of the entire material or structure. It's a critical concept because it represents a catastrophic mode of failure, often resulting in the total collapse of the element involved. What's important to understand here is that general shear failure typically happens under conditions where the material can no longer sustain any additional shear load, causing a rapid and unstable failure process. This is different from partial or local failures, which might involve only a small part of the material. In the context of our overall theme, understanding how materials and structures behave under various stresses, recognizing the signs and conditions that lead to general shear failure helps us design safer and more reliable structures. It underscores the importance of ensuring that shear strength is adequately accounted for in our engineering calculations and safety margins. So, in summary, general shear failure is a critical failure mode that we must always be cautious of, especially in high-stress environments, because it can lead to sudden and complete structural failure. Today, we're going to discuss punching shear failure, which is a critical concept in understanding the limits of reinforced concrete slabs. Punching shear occurs when a concentrated load, like a column or a pile, applies a force that causes a localized failure around the support. Essentially, instead of the entire slab cracking gradually, a small, circular or elliptical failure zone forms around the load, and the slab essentially punches through, leading to sudden failure. This type of failure is particularly dangerous because it can happen suddenly and without much warning, often resulting in catastrophic consequences for the structure. That's why properly designing against punching shear is so essential in our overall structural safety strategy. We need to ensure that the shear capacity around supports exceeds the anticipated loads, especially in areas with concentrated loads. By understanding the mechanics of punching shear, we can better specify reinforcement details and material strengths to prevent such failures. So, in the context of this presentation, recognizing and designing against punching shear is key to ensuring the durability and safety of the structures we design. Let's wrap up with some general guidelines for footing design based on soil types. When dealing with footings in clays, the primary concern is the overall shear capacity. It's important to understand that clays tend to have a relatively uniform shear strength, so we focus on that aspect for stability. Moving on to dense sands, which are those with more than 67% relative density, the key point is that they also require consideration of general shear, similar to clays, because their dense nature provides substantial shear resistance. Now, for loose to medium dense sands, with a relative density between 30% and 67%, the situation changes a bit. Here, local shear failure becomes more critical because these soils are less stable under load, and failure can occur in localized zones rather than the entire footing. Finally, in very loose sands, less than 30% relative density, punching shear is the primary failure mode. This means the footing can punch through the loose sand, leading to a sudden and localized failure, so special attention must be given to this condition to prevent such failures. These guidelines help us match our design approach to the soil characteristics, ensuring safe and efficient foundations across different ground conditions.